Okay, so the last part of this chapter, and what we're going to be looking at is just angular momentum. So you may remember earlier in the chapter we were looking at the inertia, rotational inertia, which is represented by the letter I, capital I, for various objects. Okay, now the idea with angular momentum is, just like a regular object has momentum that is mass times velocity, there's also a rotating object momentum, and that's called the angular momentum. And that is represented by the letter L, because it looks like an angle. And it is a combination of I, the rotational inertia, and omega, the rotational velocity. Now, mathematically, it turns out to be, for a ball on a string, just mvr. That would give you the rotational velocity. So if it was regular, rotational momentum. If it was regular momentum, it would be mass times velocity. So you can see there's a mass, there's a velocity, but now there's an r component too. And it would be different for the different shapes. So remember, the rotational inertia for a ball on a string was mr squared. Okay. All right. So, but other objects were like 1/2 mr squared and so on. So anyway, so this could change for different objects. Now here's a bicycle wheel, and if we were in class, I would do this bicycle wheel gyroscope idea. The idea that as this rotates, this bicycle wheel, the one we have in class, we usually wind with wire around its edge so that it has a lot more mass. And so once it starts to get going, then it wants to stay going, right, for a long time. It's got a lot of rotational inertia. And this actually allows you to do tricks, like you put someone in a spinning, on a stool that they can rotate on. And when they move the bicycle wheel, the stool will rotate them. And so there's a lab you're going to do where you get to play around with that idea. But the idea is that there is something called conservation of angular momentum. So when there's conservation of angular momentum, just like conservation of regular momentum, then a situation may change, like we had collisions, right? Two balls hitting each other. There was a before and an after momentum that should be the same in a collision. In this case, what's happening is the object usually changes its shape. So we've got someone with their arms outstretched, and they start to rotate slowly. So this is something we would do in class too. Start you rotating slowly, and then have you bring in your arms. And what happens is the rotational velocity increases. Okay, so at first with your arms outwards, you have a larger rotational inertia because your mass is further away from your body. Then as you bring your arms in, your rotational inertia goes down. But we have to keep the two sides balanced. So what happens is that your rotational velocity goes up. Okay, so that's the idea here, is you start slow. So you had a large rotational inertia, you had a small velocity, then you have a small inertia, and you have a large velocity. So everything balances out. Okay, so this is what happens when you have people in sports who start to do spins. So like we've got the classic ice skater here. She's pulling her foot way up above her head and her arms so that everything is close to the center of her body, and she can spin very fast. A diver, they want to curl up so that they can do spins. Here's a snowboarder, and sometimes they reach down and grab the bottom edge of their snowboard so that they can spin faster. So bringing the mass more towards the center allows a person to spin greater greater velocity because the rotational inertia is less. Okay, so here we've got a skater spinning on the ice. She brings her arms and legs closer to the center of her body. She changes her rotational inertia to 2/3 of the original value. Okay, so what we know is that she had some rotational inertia and she's going to decrease it, right? To 2/3 of that original inertia. So we don't know what it is, but we know it's 2/3 of it. And we know what's going to happen is that's going to change her rotational or angular velocity. So her velocity was 4 rotations per second. So our question is, what is her new velocity going to be, or rotational? Should make that a better omega. Okay, so that's what we're trying to find. What is her final rotation? I guess I should call it 2. All right. Okay, so what are we going to do here? Well, you can see how I is on both sides. So we're going to cancel that out. Okay, and so now we're going to have 4 equals 2/3 omega 2. That's what we're trying to find, that final rotational velocity. And so to get rid of the 2/3, of course, we want to multiply by 3/2 on both sides, multiply by the reciprocal, and so that gets rid of this, and we end up with omega 2 is going to be 4 times 3/2, which means that 4 over 2 is 2, so we're just going to end up with 6 rotations per second. Okay, so she has now spinning faster, which is what you'd expect. So smaller rotational inertia, greater rotational velocity. And so when people do this, part of being a gymnast or an acrobat or a snowboarder is learning to control this so that you can come out of your curling and spinning just right. So in the Olympics, there's a lot of more credit given if you can land perfectly upright for your dives or your gymnastic events. Now, cats, you've probably heard, can land on their feet when they fall. Well, they don't always land on their feet, but usually if they have enough distance to fall, they actually can. So they actually have to fall from a higher location. So there are lots of YouTube videos of cats not falling gracefully off tables and stuff. But this is an experiment where no doubt no cat was harmed in this, where the cat was innocently walking across a branch when it probably the branch rotated. Okay, so anyway, so the cat falls. Now, the thing is where you and I would be going, ah, and screaming quite a bit. The cat, look at this intelligent creature, his head is pointing and he's looking towards the ground. The other thing that's happening is that the cat pulls in its front paws and spreads out its back paws. And part of what's happening there is by spreading out its back paws, it increases the rotational inertia. It also has flaps of skin that help to, so it can use air friction as part of the force that it's working with. Now, by making the paws closer in the front half, it's able to have a smaller rotational inertia in the front half. And so it actually rotates the front around. The back had a large rotational inertia because the paws were outwards. Now it pulls the paws together. Once it's got the front rotated, the front paws go out, the back paws go in, and now it rotates its back end around. So it does the front end against the back end. And so now the cat is rotated all the way around, and now it can land on its feet. So given enough room to fall, yes, a cat can land on its feet. Okay, so, and that has to do with rotational inertia. All right, so that's all we're doing in this section. Okay. Okay.